So, welcome everyone. My name's Ben Wilson, and
I'm Todd Plantinga. I work with FLAIR, which is FireEye Lab for Advanced Reverse Engineering.
And I work for the Advanced Practices Adversary Pursuit team. So today, we're going to talk about rich headers. What we're going to cover is a technical overview of them, what they actually are and their structure, how we're actually using them here at FireEye, and how we sort of think you should be as well. And we'll sort of, throughout the talk about why, which is essentially to help you find more evil more efficiently. So more specifically, what is this funny little 80 bytes at the top of a executable file? What can it actually tell us? We're going to talk about how we can decode it. We're going to then talk about some of the maths around our statistical analysis of a very large data set of malware and using these across it. And we're going to then give some tales from the trenches about what we've actually, some of the cases we've used it in the wild and some of the wins we've had with it. So first of all, why are rich headers even? Why do these things exist? They've actually been in executable files since 1998. They're an artifact that is left in there when you compile a binary. It's been a lot of tinfoil hat theories, and when they were initially discovered around, oh my God, this is Microsoft putting some sort of tracking beacon in our files, and what is this thing? Because no one really understood it. It wasn't a documented format. Despite these sort of tinfoil hat theories, though, I've been digging through some old Microsoft patents and things like that and looking at the reasons behind these. And the most likely explanation is that these are actually part of linker and compiler optimizations and not the sort of malicious intent that some people assumed. That said, we're going to talk about how we can actually use these, or rather misuse these from their original purpose for the purpose of actually fingerprinting binaries. So there's a growing body of knowledge around these. One of the first public papers was in 2004 on this, and since then there's been bits of articles released where people have gotten further and further with actually decoding the protocol and figuring out what it means, and we're sort of now in 2019 and we have quite a rich body of knowledge about these, and we're hoping to contribute to that sort of body today with our talk. So, how the rich header is actually made. This is going to just be a quick breakdown of what it actually is. So most of you have looked at executable header in a hex editor at one stage or another, and you've probably seen these first few bytes in the file and maybe even just disregarded them. We have our standard DOS header. We have within that a pointer to the coff header, and then between those two, we have the rich header, which you can see is got a footer with the word RICH, and then 4 more bytes following it. So essentially that rich header, if we look at how it's actually composed in the first place, we take the clear version of that rich header, and we also take the DOS header from the sort of MZ string all the way down. And we basically take those two bits of data, we XOR them, and we end up with this key that goes at the end. And that 4-byte key is both a checksum that is used to validate that the data hasn't been tampered with, and it's also the key we can use to decode that header. So for those of you who are familiar with tools like CyberChef, really easy. You can just drop in a copy of the actual rich header, drop in those 4 bytes behind the rich key, and you get a decoded version of the rich header itself. And you'll see that by the DNS header in the output there is kind of indicative that you've managed to reverse it correctly and it hasn't been tampered with. If you don't get that, then that's quite likely someone's actually changed the checksum. We can then take a hash of that cleared version of the rich header, and we'll talk about how we can maybe use that hash later on. But what I want to quickly discuss then is how is that clear version of the rich header made? So if I now take that data that I've decoded, and you can see a few things here. One, it starts with DNS, which is the string I mentioned before. 2, it's made up of these 8-byte units we call comp IDs. And each of these 8-byte comp IDs represent an import that was imported in the original source code. It's comprised then in these 8-byte keys of 3 pieces. The first one is the compiler product version. So this is the version of Visual Studio, basically, that was used to actually compile this executable. And it's all the way down to the minor revision number. So we can get a fair bit of information about the developer's workstation and their Visual Studio setup. It's also got a semi-unique product ID, which is reference to the actual lib or ASM or obj file that was actually imported to the source code. And then finally, we have a reference count, which is the number of times that library was actually used within the source code, within the program. And so what we end up with is a fairly unique key of each one of these. Then we combine those, within most executables, they have anywhere from sort of 1 to about 12 or 13 of these. And so that starts to form a bit of a unique fingerprint. What's also important here is the actual the actual order of these that they're in, because that order actually matters, as we'll discuss later as well, because it reflects the order in which those were loaded into the binary in the source code as well.
All right, thank you. So I get to work in the back end of FireEye where we have lots of data. I get to do some analysis on that data. And for this project, I'm going through one of our data repositories. We call it Nucleus inside the company. And it's all malware or suspected malware. We have several million samples of this. And so after I cull out .NET and Delphi samples, because they don't have a rich header, I had 5.7 million samples, as you can see up here. I'm going to give you the results now. When we processed this, computed the rich header hash, and some other properties. So the main question I want to answer is the rich header worth our time for finding evil? Typically what you want to do, I've got a new sample, it has a rich header. Can I find other samples of that same rich header, and do I learn anything by pivoting on that? I'm going to answer that question on this large scale. Is it usually helpful? Is it any better than using the import hash? That's probably an established technique for many of you. I know it is inside FireEye. Is this a better way to do it? Is it different? And is it specific to code families, which is the most important thing we want to know inside FireEye? So the first question, is it useful? This graph shows a count of how many samples a pivot will match, a rich header will match when you pivot to it, and this is a total for it. So it's a count of how many rich header hashes had 2 samples, how many of those had 3 samples, 4 samples, et cetera, marching down here. So the upper left point on that graph says that 8.9% of our samples have a rich header hash with no match whatsoever. It's just a unique rich header hash, singleton, no good for pivoting on. And on the lower right-hand side is the other extreme. We've got a couple of hashes which are super common. The most extreme one out there has 242,000 samples matching it. It happens to be Visual Basic 6. It's only got one of those comp IDs inside of it, and it tells you it's a version of Visual Basic 6. So that's no good for doing any further work either. There's kind of a sweet spot where you have, say, 2 to 200 pivots. I picked that arbitrarily, but that's kind of a useful set where you could go look at those samples and figure something out. And that encompasses the green bracket there, and about a third of the samples fit in there. So it is useful to find about a third of those samples. And, oh, and by the way, if I were to make a similar plot for import hash, it would look just like that curve. Or PE compile time date stamp. Most of the indicators of compromise have that same kind of distribution. So it is useful. Now I want to compare it to import hash. So they both kind of reflect the compile time tool set in a sense. You might expect there is something in common with them. So the way to approach this mathematically is by clustering. So you can say I've got my 5.7 million samples, and I can cluster them using import hash. And I've got my 5.7 million samples, and I can cluster them by rich header hash. And we want to know, are these clusterings the same? Do they have a lot of overlap? That'll tell us whether it's useful or not. So there's a couple of statistical ways to do that. You can calculate the mutual information or the adjusted RAND index. And I did that, and it says there's a fair amount of overlap there. But I wanted more insight than just that single number. So we're going to go through some examples here so I can give you a really precise insight on it. So this is real data, snapshots with our Nucleus tool from the 5.7 million samples. I picked an import hash here, and there are exactly 4 hits on that. And you can see on the right-hand side that all 4 of these samples had the same rich header hash. And I checked, and these are the only 4 samples with that rich header hash out of the 5.7 million. So I say that these are exactly equivalent. The information from the rich header hash is redundant. It's not learning anything new about that. That's one case. Another case is an import hash. In this case, I have 11 samples, and it matches 3 different rich headers hashes. And again, these rich header hashes are totally specific. No more of them exist in the database. So I can identify this cluster of 11 samples either with a single import hash or with the 3 rich header hashes. Generically, I'm going to call that, you see in the lower right-hand corner there, one-to-many for the import hashes to the rich header hashes. And then there's kind of the converse of that case. Now I've got a rich header hash. It takes multiple import hashes to match up with that. Again, they give me exactly the same cluster. And then there's a final case where you can't match up the clusters. So like in this example, if that top sample, that particular import hash, happened to match another sample with a different rich header hash, there'd be no way I could get those 2 clusters to line up. So that's the other possibility. So with that in mind, Computed this for the 5.7 million samples, all the clusterings. These top numbers are starting from the point of view of the rich header hash. Can I match it with import hashes? And the bottom is the reverse of that. So the first line of this data, 27% of the samples have that exact match. 20% of the time, it's that redundant information. I'm not adding anything new with rich header hash. But then the second line, 48% of the time, one rich header hash can be explained by multiple import hashes. So combining that 75% of the time, 3/4 of the time, you can detail a cluster by rich header hash or by one or more import hashes. The bottom side is when I start with import hash, and you see it's far different. It's much more rare that one import hash will have multiple rich header hashes. So what does all this mean? It suggests that 75% of the time, the malware author is using a tool set, the same tool set which we characterized by that rich header hash, and he's changing the imports. He's generating different binaries with different imports. But it's the same guy because it's exactly the same set of samples by that set of many import hashes as the one rich header hash. Excuse me. And that in turn suggests that if you've been doing your hunting for similar samples by import hash, you should broaden your search and look at rich headers, because it's a very interesting set. It's specific 3/4 of the time to exactly the same guy building that malware. And Ben will give you a lot more compelling special cases for that. I can do the same sort of analysis for code family. So think now of my 5.7 million samples with code family tags, except we don't have 5.7 million tags. It's more like 300,000. And let each code family be a clustering, and can I match that up with import hash? And the big number here is on the very bottom there, where you see that actually more than 2/3 of the time I can do that with one code family matching to multiple, one or more rich header hashes. So it is useful for code family. And I don't have a plot showing this, but it also works very well for threat group. We have even a smaller number of those. It's not quite as statistically significant. But it's a really strong indicator in 2/3 of the cases here of the code family. OK, so I want to make a little mention of tampering with the rich header. It's not essential for execution of the code. You can mess with the rich header, and it doesn't change the functionality of the sample. And bad guys are going to learn that we're doing this and start changing with it. So we looked for several different cases where you could tamper with the rich header. I only have time to talk about one of them here. It's going to be tampering with the rich header checksum. So the checksum, which Ben went through, is the thing at the very end, which lets you apply as an XOR decode to get the contents of the rich header. You work your way back to that pre-footer DANS, that prefix DANS bytes. But we know how to compute the checksum. It uses the DOS header, except for those 4 bytes, as he pointed out, and it uses those contents. So we can check after we decode it to see if it matches. And I find 5.4% of the time in these samples that it doesn't. The match doesn't, checksum does not equal it. So what's going on? And one of the suspicions here is that it's the DOS header. So I have to start taking a look at the DOS header, which is something I normally take for granted because it shows up in this case. So there's kind of a normal DOS header. I've never looked at these before, and maybe you don't either. The first 60 bytes, you've got the MZ, and then just kind of boilerplate stuff. There's the 4 bytes, which can change. That's not part of the rich header hash. That's the pointer down to the cough header. Then the second 64 has got that usual DOS stub that you're used to see. This program cannot be run in DOS mode. That's kind of the normal thing. But you can have modified ones, as I show in the example down below there. Lots of modified cases. So to get a better handle on this, I took 20,000 specific samples that had that tampering, where the checksum didn't match up, and discovered that 70% of them, I could get the right checksum if I restored to that normal DOS header. That normal DOS header is something you see in most of the time. I don't have an exact count on that yet, but I'm working on getting that through our 5.7 million samples. So you can fix that with a DOS header. That means they've messed with the header. So in all likelihood, the malware author compiled the sample with MSVC, got a correct rich header, then went and altered the DOS header, putting bytes in there, forgot that that messes up the checksum, and we detect that as a tampered checksum, when really it's a tampered DOS header is what they did with. And our colleague Rick Cole, when I told him we were having a discussion about this, told me, yeah, Metasploit does exactly that. And so it's at the bottom. It's pretty hard to see there. But this is actual source code from Interpreter Loader, where they are taking the shell code and hiding it right after the MZ at the top of the DOS header. So we see that as a tampered rich header checksum, but really they're just hiding stuff up in there. And that accounts for about 1/4 of that 70% there. There's a lot more to say about that, but I don't have time to get into it. You can talk about me more. And now Ben's going to give you some really interesting case studies.
Yeah, so like I said, we'd like to cover a few of the use cases where we've had some wins with rich headers. So one example was APT41's loader, EasyNight. And this is an interesting loader because what we had is around a bit over 100 samples that we had classified as this piece of malware within our data set. And that means that an analyst has actually looked at that bit of malware and made that call on it and tagged it as such. When we pivoted on our data set with that rich hash associated with these different loaders, what we actually found, we ended up with nearly 220 samples. So why this sudden growth in samples? There were obviously some that just were within data sets that hadn't been tagged, but quite a few of them showing up were actually legitimate Microsoft executables. And we're sort of going, okay, so what's the go there? And what became obvious is that what they do with EasyNight is they actually don't make their binaries just look like Microsoft executables. They're taking the actual Microsoft executable and they're patching the actual loader. So they're patching the RVA table within the binary and adding in an extra import. And that extra import becomes then quite obvious when you start looking at this data in this manner and pivoting by rich headers. So as you can see within the examples here, all the malicious ones are in red and they have this additional import that you can see. And so the great thing about this is that it's them trying a technique to really blend in and make their executables look like they're legitimate. But what they've actually done is given us a nice big red flag that we can identify those particular malware samples because, you know, it's such an obvious thing when you compare it to the legitimate executable it's based on pivoting on a rich header. Similarly, they've been doing a similar thing with EasyDay, which is like EasyNight, except starts to add in some extra steps to decode the executable taken from the actual loading executables file. So for us, this is a nice way of finding some of their malware. Also some cautionary tales. So one thing we were looking at where we found a rich hash across several malware samples that were all attributed to a bunch of what we suspect are Chinese-related threat groups. Now, what our initial thoughts is maybe this is a shared loader that is across all these samples with variable payloads. And so we've seen things like that with EasyNight, and we see other loaders from a number of groups that we track that do this. You know, could it potentially be a digital quartermaster that's building tools and distributing amongst these groups? Is another possibility. But in fact, we turned out that this is actually just an SFX-RAR packed executable. And so a bunch of packaging utilities like this, same with Pi2Xe, NSIS, and the like, are going to end up with the same rich header in something. So I guess the cautionary tale out of this is that analytical bias is easy to introduce with doing some of this analysis. If you don't have a big enough and rich enough sort of data set with both goodware and badware, you might make some analytical leaps based on your observations of a rich header appearing in certain files, but you know, you do need to verify that when you're looking at these. One other really neat thing about rich headers is that there's a lot of packers out there that will do all sorts of things to obscure the file content and strings and make the sample look nothing like the original unpacked sample. Quite a few of them, however, don't actually touch the rich header at all. And so what we found, we were looking into an UNC403 sample of cookie clog, which is a family we've traditionally seen used by APT20. It was much different though. It had many more imports and was obviously packed, and it was packed with a safe engine packer. But what rich header analysis allowed us to do was quickly illuminate the fact that it actually shares a rich header with all the APT20 samples that we've been tracking as well. So that's an interesting analytical finding. You know, it's certainly not strong enough for us to say that they're necessarily the same thing, but it is an interesting analytical point of view for us to take on samples when we see these overlaps, and contributes to, you know, maybe down the track being able to merge these groups to the wider groups. So we mentioned before that if we take the clear version of the rich header as we've extracted it and we simply hash it, that hash is what we kind of refer to as a rich hash. And it's become a bit of a de facto pseudo standard that we use. So for example, the Yarra PE module now can simply take that hash and you can build a Yarra rule straight like that to find other related samples that share the same hash. That's really good and really effective, and we've had a lot of wins from that. But one other thing we've been doing a bit of research on as well is similarity matching of the hashes. So obviously any single byte changes within that rich header, and it's going to end up with a completely different hash. So similarity matching is important because there's a lot of factors that can change just a single byte in there. So for example, adding a single extra import could do that. So there's been a few approaches. There's a really great paper, Rich Header Analysis and Hunting on RopGadget, where they took a number of different approaches to this. So one is just ignoring the count from the actual imports and just focusing on the product ID part and the compiler version as a tuple, and then simply looking for those same tuples across all rich headers as a cluster. That's got a few shortcomings because often we see, and the example I'll talk about, where those over time can actually change. They can remove imports, add new imports, and the like. Second of all, it ignores ordering, so it's going to be much more prone to things like false positives because there is scenarios where those are going to appear in the same file, but the actual ordering of them matters. So the second approach they take is doing actually an ordered search for those, and basically what you're doing is looking for those same comp IDs in the same order within a file, and that's actually more effective, but it does, again, have a few shortcomings, especially when we see some of these imports removed. It will then fail and give you a false negative. So by way of an example, SLOWROLL is a malware family we track that's related to a financial crime group, and this is just 3 samples we've taken from recent times. So the one on the left is from February this year. The one in the middle is from March, and the one on the right is from June. And we can see actually the evolution of these malware developers as they've evolved this malware family through looking at the components of the rich header in the clear. So we can see from the first to the second sample, there was a couple of changes. One, the count changed on one of the imports. And 2, it looks like they removed one of the actual imports and replaced it with a different one, but it has the same count. So likely that has the same function. It was just a later version of that imported library or something else that they used. So then we see from the February to the, from the March to the June sample, quite a few changes. So one of the big ones is you'll notice the compiler version has actually changed. So we know they went from a certain version of Visual Studio to a later version. And so that means that we're showing not only is this under active development, but also they're taking their workstation they're developing this on and applying patches and upgrading it as they go. And we also see they've added in a few more imported sections and a few more libraries that weren't there before. So this is where a lot of the traditional rich hash analysis would fail, and even where we need to have some considerations around how to do similarity matching to catch these types of scenarios. So our approach has been to do a kind of a fuzzy way of looking at these, and an important component in this is because we often see malware families where they are quite modular in nature as well, and so depending on the variant you've got, there may be some core functions across all of those, but then some may have additional functions plugged in and additional modules plugged in, and they're going to show up as different artifacts in the rich header. And so only by analysis of sort of a wide enough range of samples can you start to see those patterns within the samples. And so this is where we're quite fortunate that we have a huge data set of samples we take from our intelligence gathering, we take from our managed defense and our intrusion response work, as well as from all of our appliances and endpoints. And so that allows us to really have some great data to work with to be able to draw some of these conclusions and be able to build these kind of rich header analysis where we can start to fingerprint the common components across that entire family. So our approach, there's kind of 3, I guess. One is that we can take an automated approach and we can just extract rich hatches that we know are in particular malware families and are a reliable indicator of that family and search for them. The second one is we can search for ordered comp IDs, so similar to the method we discussed before, except what we actually do is do multiple permutations of the set that we'd get. So ones where we'll remove certain imports and ones where we will actually account for things like the order of the imports swapping by one place, which is a common observation we've seen as well. And then the third one is just simply manual code analysis of the actual clear data of the rich header to look for common patterns and then sort of handcrafting Yarrow rules to appropriately suit them. So that's really the end of our talk. I guess the real points we want everyone to take away is that rich headers are really useful as a quite unique compilation and linker artifact. They're absolutely useful for things like speeding up malware family triage and identification. They can be circumstantially related to threat actors, but obviously that's more from a perspective of overlap rather than attribution. And they are really a supplemental indicator that are really effective when combined with a number of other static or dynamic techniques or even reverse engineering. As Todd discussed too, the tampering is not 100% foolproof, and there have been cases discussed in the wild where people have intentionally tampered with rich hashes to actually try and fool attribution. So really our ask is that everyone starts using these more, and that when people are sharing indicators of compromise as well, that maybe we should all start looking to share rich hashes as part of that, because they can be more effective to find related samples than just a straight file hash. And that's the end. Thank you very much.